look at an example. We are looking at 1 minus x squared y second minus 2x y prime plus y equal to 0. By now we have seen y and y prime and y second written as power series. We are looking at x not equal to 0. This is an ordinary point. 1 minus x squared computed at x equal to 0 is indeed different than 0, so we're good. The other thing that we want to compute is what is x squared multiplied by y second, because we need that in order to plug it in the ODE that we're looking at. So we want to compute the sum from n equals to 2 to infinity of an n minus 1 x to the power n minus 2 multiplied by x2. And this simplifies nicely, so we only have x to the power n. We also would like our sum to start at n equal to 0. Is that a problem? It's not, because n equal to 0 makes our coefficient equal to 0, because we have an times 0 times n minus 1. N equals to 1 also makes our coefficient equal to 0. So we can start this infinite sum at n equal to 0 with no problem, because the first two coefficients are just trivially 0. In the same way we can do for y prime, we can either shift the coefficients or just notice that if you consider n equal to 0, the first term is equal to 0. But we don't want to do that, because we want, remember, the power of x and the index to be the same thing. Now that we have computed everything, we plug it in. We have 1 minus x squared y second that becomes sum from n plus 2, from n equals to 0 to infinity of n plus 2 multiplied by n plus 2 times n plus 1 multiplied by x to the power n, plus we have x squared y second, so it is infinite series from n equal to 0 to infinity of n times n minus 1 x to the power n. Then we have minus 2x multiplied by y prime. Minus 2x is a sum from n equal to 0 to infinity of n plus 1 multiplied by n plus 1 x to the n. And then we just have y, that is sum from n equal to 0 to infinity of n x n. So you see I'm showing you two different approaches to compute powers of x multiplied by power series. This is nice because most of the terms we now have are sums that go from n equal to 0 to infinity and the power of x at the end. The only term that does not satisfy this is a term that goes 2x times the power series in the right format. This is a problem, so we're going to work on it a little bit. And we have that if you take inside the 2x, or the minus 2x, you have a sum from n going to infinity, from 0 to infinity of minus 2a at the n plus 1 multiplied by n plus 1 at the power, multiplied by x at the power n plus 1 equal to 0. So you see everything in here has indices n plus 1. So we can shift these indices and retrieve n equal to 0 to infinity of minus 2 n x to the n. What are the middle steps? Well, first we changed having a sum going from n equal to 1 to infinity, and instead of n plus 1, we only have n. And then we notice that we're multiplied by n, so we can take the series starting at n equal to 0. Now we have something in which every single term has the format that we want. A sum from n equal to 0 to infinity times a coefficient that is maybe very complicated times x to the n. So we put all these coefficients together and we have the same format, a sum from n equal to 0 to infinity of all the coefficients of all the power series that we have built until now together multiplied by x to the n. Remember, you can do that only if the indices of the sum are going from the same value to the same value, in this case 0 to infinity, and if they correspond in the same way to the power of x. In this case, x to the n. So we can do this, and we retrieve a recursive relation by just setting the coefficients, every single coefficient of our infinitely long power series, we have to set it to equal to 0. Otherwise, the power series itself is not equal to 0. So we have an plus 1 times n plus 1 times n plus 2 plus an times a big parenthesis n minus 1 plus 1 minus 2n equal to 0. And we can solve this in the format of an plus 1 equals something that depends on n times an. This is the recurrent relation we want. Again, we are lucky. We have an plus 1 that only depends on an. So as for the previous case, when we're computing, we're jumping from even to even number and from odd to odd number. Sorry. That means that our fundamental solutions are easily unentangled. On the other hand, we cannot write them as nicely as a sine and cosine. They're going to stay in the format of power series.